Okay, so in previous conversation and reading, we learned that we could calculate angular momentum using this quantity I times omega, I being the moment of inertia and omega being the angular velocity. What I want you to start thinking about now are these two statements here. We can then write the total torque as being the rate of change of the angular momentum. So if you take a look at that, what it's saying is the net torque is equal to the change in angular momentum over the change in time, because we're talking about a rate of change. All right, so think back. Really, this is the same thing as the impulse momentum theorem. We learned that a force, a net force, changes the linear momentum of a system. So net force is the rate of change of linear momentum, P, with time. So essentially that statement, guys, is the impulse momentum theorem, just in a rotational sense. Okay. And if the net torque on an object is 0, the total angular momentum is constant. So you want to basically think about this situation as being like, okay, is this a situation where there is an external net torque acting on the system or not? If there is, then you could say the net torque equals I times alpha, which we've already discussed. Or another way of saying exactly that same thing is change in L over change in T, or the rate of change of angular momentum. So this statement and this statement are the same. Okay. And the opposite of this is also true. So if there is no net torque, then there is no change in angular momentum. So if there's no external torque, then the angular momentum you started with has to be equal to the angular momentum that you ended with. Okay, and we saw that in the demonstration. So here's an example problem that kind of goes along with that. It says a person stands with his hands at his sides and rotates on a platform at 1.3 revolutions per second. If he raises his arms, his rotation rate decreases to 0.8 revolutions per second. Why does this occur? And by what factor has his moment of inertia changed? Okay, well, let's talk about the why first. When he pulls his arms in, or sorry, raises his arms, we're doing the opposite. When he raises his arms, he's pushing more mass farther away from his axis of rotation. So he's increasing his rotational inertia. But moving his arms in and out doesn't constitute an external torque. So his angular momentum has to stay the same. All right, so here's what we know. He started out at 1.3 revolutions per second. He ended at 0.8 revolutions per second. And there's no external torque. So I could say the angular momentum he started with has to be equal to the angular momentum he ends with. Angular momentum of a rigid object is I times omega. So I do his initial rotational inertia times his angular speed equals his rotational inertia at the end times his angular speed at the end. The question asks by what factor has his moment of inertia changed. So I want to know about his moment of inertia at the end. So I need to isolate I final here. So I divided both sides by omega final, and I got this expression. I don't know what I initial is, but that's okay because they're asking me by what factor has it changed. So I'll just leave it as I here, I initial. We have an initial angular velocity of 1.3 revolutions per second, a final angular velocity of 0.8 revolutions per second. So if we divide those two, we get 1.625 times the original moment of inertia. So his moment of inertia has increased by a factor of 1.625. So this is just kind of a simple example getting into what we saw in the demonstrations and some of the other stuff that we talked about.